In this video, we are going to look at the application demo in which we are building a traffic sound recognition system using Keras API and deep learning. Nowadays, since advanced driver assistance systems are becoming more and more popular, it is important to have a proper traffic sound recognition program software which can detect traffic signs accurately and will help drastically in recognizing traffic signs and decrease the number of accidents occurring on the road. Building a traffic sign model consists of different steps. First of all, we have to compile a dataset. The dataset which we are using is known as the German Traffic Sound Recognition Benchmark, and it consists of approximately 50,000 images. The images are classified into 43 different classes, which are different speed limits, and the entry in the vehicles is different traffic signs. And we have an ID in the range of 0 to 42, which represents 43 different classes. So we'll look at some of the images in the traffic sign recognition benchmark dataset. So here we have two different folders, one for training and one for testing. And here we can see different images of traffic signs, but one problem with this dataset is that the images have a bad contrast and they are quite blurry. And to solve this issue, we'll have to apply histogram equalization to increase the contrast of these images. Here, this graph demonstrates the different traffic signs, the different classes, starting from 0 to 42. And here, it shows a different amount of images per class. But as you can see, some of these classes have around 200 images, while others have around 1500, 2000, and this results in the skewness of the dataset. And it is bad for training using such a dataset, whereas we have to solve this issue by using different weights when training the different classes. The next step consists of dividing the dataset into two parts, one for training and one for testing. In this case, we are using 80% of the dataset for training and the remaining 20% for testing purposes. This makes it around 39,000 images for training and around 12,000 for testing purposes. Before training the images for feature extraction, the images in the dataset have to be preprocessed first. That is, they all have to be converted to the same size, and histogram equalization should be applied to increase the contrast of the image, and then these images can be passed to a neural network for training. For the training purposes, we're going to use convolutional neural network, CNN. In this case, we are going to have different layers of convolution, followed by activation, batch normalization, and max reading layers. And the first convolutional layer consists of 8 filters, each one being of size 5 by 5. The second layer consists of 16 different filters of size 3 by 3. And the last layer consists of 32 filters, which are also of size 3 by 3. After passing through the convolutional layer, the image is passed to the batch normalization layer, where it is normalized, and when it is passed to the max reading layers, where downsampling occurs. Then, after training our model, we are going to evaluate it against a test set and determine how well it is performing. And then later we are going to try to predict images and see whether they are producing the appropriate results. Now we'll have a look at the code. Here is the training code. First of all, we have a function in which we'll give it a path and a CSV file, an Excel file, and it will extract the images from that path. We'll use this function to extract the testing and training images. When running this code, we also have to pass arguments. We'll have to pass arguments, the path where the dataset is stored, also the model, the path where we want to store the model and how we name the model. And these two are compulsory, and this one is not compulsory. It is a path where we store the graph obtained after training, the plotting of the graph. For training the environment, we are going to train it for 30 bucks with an initial learning rate of 1 exponent minus 3 and impact size of 64. First of all, we are going to learn the names, the label names, which is in this file, the different sign names, so speed limit and so on. And then we are going to load the training and testing images by calling the bundle function and calling this function, and it will return us two arrays, one for data and one for labels. After that, we are going to normalize these images by dividing it by 255. Then we are going to encode these images for training purposes and also assign weights when training, since the dataset is skewed. We'll also apply image augmentation on the different images by rotating it or applying different types of transformation to it, as training with different types of images will produce better results. Afterwards, we are going to load our model, which is a traffic sign net model. In this one, we use a sequential API for the model, and we have the different convolutional layers. First one, second one, and third one. And then we are going to apply normalization box ruling after each convolution. Afterwards, we are going to compile our model, and then we start the training process here. After the training process, we're going to evaluate our model using the model.predict, and then we'll save the model on the disk for future use. Now we'll have a look at the code. Now we're going to load the code to execute the training code, where we have to pass the path of the dataset and also that where we want to save our model. So we'll run this code now. And it will do the training and testing images. As it takes quite a long time to load all the images and the training purposes, I want to export in this video, but I will use the train model obtained for the prediction and measure of accuracy in two different files, two different programs. After the training process, we are going to have the same model here, and we use this model for evaluating our model and for prediction. Now let's have a look at the evaluation code. So we have to load our model as shown here, and then we train all the testing images will spawn here, and then it will try to predict these images and compare it to its result. After having learned the model, we learn the images and store them in an array. We have to perform the same processing like to perform a training. How to normalize the image, reshape it, and then we use the model that predict function to test or to predict the classes of each image. I'm going to execute the code now. Here it will learn the images first. Okay, it is going to extract the images and takes quite some time. And afterwards it produces different and gave us the evaluation of the model. Shows that it has an accuracy of 95% and a F measure of 0.92, which is very good for the traffic side prediction model. Next we see the prediction code where we're going to predict images, and instead of only predicting images from the command line, I have built a simple GUI where the user will be able to select an image from his PC and then it will predict it and display it. So here it will take the path which the user has selected, convert the image to array, resizing it to the same shape as the model was trained, and normalize it and changing its shape, and then use the model that predict function to predict the traffic style. We'll look at the code now. So running the code now. We're going to have a GUI where the user can select a photo, a picture, see here, and then click on the classify button and we will obtain what traffic zone it is and try it for different images here. And so different examples. Even when the image is white, we can say blur. It has a proven trusted since we applied histogram recognition and different preprocessing techniques before training the neural networks and that's it for this video.